Okay, well, routing is probably the last one that we'll do the full thing on. We'll be skipping things that are in wireless networking and WANs, and policies and procedures will just have a little, because I want you to focus on the main core of what networking is. And then in the next class, as you know, that'll be ethical hacking in the next class, and we'll go through a bunch of stuff there. So if you're interested in the Network Plus certification, then you'll have to go through the rest of these on your own and do these tests at the bottom, Network Plus practice exams, to get yourself honed in and ready to take it. But you'll definitely have the core, most difficult portions of the learning down. The rest of this with hardening sounds absolutely awesome, but when you look at it, you'll see what they mean. This is why I'm doing ethical hacking instead, because as far as security goes and hardening, these are really generic and not very exciting. There's just some facts you got to remember and do. Same with management and optimization. Good stuff in there. I'm not saying that you wouldn't use it, but when it comes to, I need to understand what's happening on this network. Really, that ends with routing, a little bit of firewalling, and of course wireless networking. And there's a little bit in WANs, but WANs are so specialized, I'll probably just leave that out. You can look at it if you want the Network Plus certification. So let's dive into what routing does for us. Routing facts sheet obviously is going to be really, really important. At layer 2, we deal with frames and we deal not with packets, but again, Ethernet frames. That's what we call them. The term packet is used with IP, and when we get to routing, then we start talking about routing packets. So when you think about what happens in Ethernet, that piece of information that we call a frame gets sent between one place to another. Now maybe that's a broadcast frame and it goes from one place to everybody else, but there's still not several ways to get there, again, unless you are dealing with STP, which, as I said, lots of people just steer clear of it because it works sometimes and doesn't work other times. But when you get to layer 3, the internet is all about routing. It's all about taking your 400 different packets that you just sent and throwing them out there on this network and getting them to the place that they need to get to, not necessarily following the same path. And so packets, layer 3, frames, layer 2. All right, so a packet is the payload of an OSI layer 2 frame. So in other words, what are we really doing in there? Well, because we use IP, right? Packets are what's in there. That's what we're using. So in the packet, the header contains the source and destination. So I will actually pull up a picture of that. IP packet. So let's take a look at images here. There's tons and tons of them. So this is an IP packet. That's what this is, 32 bits, and this is what is made up in there. So that's actually kind of small. I don't know if I like that one. Let's find another one. There we go. That's a little, to me, that's a little easier to read right there. And this is IP6, isn't it? Where's our, saw it someplace in there. Anyway, so this is what it's made up of. This is what's in your TCP/IP packet, the version number, total length, what it's going to be in. Source and destination, oh, there it is, protocol 6 TCP. Okay, so the source and destination address are right here in the IP header. And then the first part of the TCP packet is going to have the source port and the destination port. So if you're just dealing with an IP, here you are. But the TCP portion is going to deal with what port am I dealing with on my end and what port am I dealing with on the other end. Right? And this is not Windows right there. All right, so let's jump back over here. Sorry, it just scrolls so fast. All right, so network. When used in routing, the term network can be identified as a broadcast domain where all the hosts have the same network portion in their IP address, meaning what we've talked about before. If I say your network is 10.10.10.0, then the network is 10.10.10 as identified by 255, 255, 255. Normally a LAN fits this more precise definition of a network. So normally what they're trying to say is that you probably should use the term LAN if you're just talking about that tiny portion. But network also is used, oh, this is this network, this is the student network, that's what I always say, right? And this is the faculty network, staff network. So to perform routing, this is what a router's got to do. It receives the frame, opens the frame's payload, which is the IP packet, reads the packet header to find the IP address information, matches the destination network address with entries in its routing table, creates new frame using the packet as the payload, and transmits the new frame to the next hop. So you see that process of it taking it, looking at it, and saying, where does this need to go, identifying which network it needs to go on, readdressing it, and putting it back on the network. And that's what it does until it gets to the next hop. The next hop means that it's the next router down the road, right? The next router it's going to hit to. So, which is described here. So, router only needs to know the next hop information, not the full path to the ultimate destination. The next hop is the gateway router that the router will send the packet to. Then you have a portion of this table, right, what's in here, and that's a routing table. And the routing table is this database that's got all these entries in it. It's usually just a flat text file. It's not like a big deal or anything. And it has the address of the known network. It has the next hop gateway or router to that. It's got the network interface. That's the actual physical interface. That's like I plugged into that port and it's fiber optic. That's what they mean by interface, to reach the next hop gateway. So what interface on my existence do I need to send that out through? And then a metric or a cost that indicates how desirable it is. The lower the metric, the more desirable. So if it's a 10 instead of 100, that's more desirable. And this metric or cost could actually mean the literal cost of using that connection. But it could also mean a bunch of other stuff, like how much time does it take to get there? How many hops does it have to go through? There's a lot of things that go into this metric, as we'll see in a little while. And then, as I've described before, just like your computer, there's a default route, a default gateway. So the default route is an entry of 000 in the routing table. This entry matches every network. If no other entry in the routing table matches the destination IP address of the packet, the router will send the packet to the gateway found in the default route. So it's basically what you do in the table is you go 0.0.0.0, and then this is the actual IP of that next hop for I don't know where this goes. So that's that process I described before where your computer doesn't know where Google actually is, and so it sends it to its default gateway, which is the local router, and then the local router looks at that IP and it doesn't know where it is, and so it sends it to its default gateway or default route, and it keeps happening on all these different routers on the internet until finally it hits a router that goes, oh, that particular IP is off of this interface. And I know that, so I'll send it out interface 6, and that'll get over to that network. And then a loopback entry, which is the loopback address, and that's used for diagnostics like it is on anything else. So there's a few ways to put in routes. You can statically assign them, and usually your default route is a statically assigned route. And that's, if we bring this into reality, if we're EAC, what that means is that they're going to program their router and say, well, we actually use Valley Telecom and they've given us their router and network information. And so for our default route, we're going to put their router in, right? And they statically assign that. They type it in and say that's them. And then dynamic ones are actually built. They're built using different routing protocols. So this dynamic here is you got multiple places it can go, and instead of statically assigning all those multiple places, we're going to let it figure it out on its own. So they dynamically learn about networks by sharing routing information with other routers. When you're talking about using dynamic routing, you're talking about using the same routing protocols to speak with each other. Right? You can't use two different routing protocols and get the job done. Everybody's got to be using the same one. By everybody, I just mean the routers you're connected to. And just because you use one routing protocol doesn't mean you can't use 3 or 4 others at the same time. So dynamic routing is implemented by enabling the routing protocol. A routing protocol adds dynamic entries to the routing table, and multiple paths to networks are available. Routing protocols define the algorithm used to calculate the metric and how routers communicate with each other to share the network information. Routing protocols use the metric information to insert the best hop into the routing table when there's multiple paths. So if we were to, if I go over to my terrible sketchpad, yay, I got a whiteboard. Aren't you guys so excited? Probably not, huh? So if we say that this is Arizona's router right here in Phoenix, we'll say Arizona only has one, right? And Arizona's router goes up to Utah. So we're going to put an A here and a U here. And then we've got Colorado right over here, and it's got its own router, and it's connected like that. And then we'll say New Mexico has got a router, and it's connected. See, now we have 2 different ways to get to Colorado. As a matter of fact, as Colorado gets connected out, right, it's going off to other places, and so is New Mexico. And then we're going over to Nevada and California. You end up with a lot of ways you can get to a destination. So if these routers here are all using the same protocol, they can let each other know about these other routes. They can talk to each other about them, and then the router itself can look and say, I probably should use this one. It'll take less time to get there, and it'll use it. That's how that works. That's dynamic routing. Oops. Now, the 2 different types of protocols, if we want to break them down into, what are we doing with these protocols, is there's an interior and an exterior type of protocols. So when you look at this stuff, you really got to think of a massive network. You got to think of your AT&T, and you also connect to Verizon. And that's pretty much the US right there. And so if you're AT&T, then you may use interior protocols for your own network and then an exterior protocol to actually talk to Verizon. So they have different uses, and some, you're going to find out that some protocols are both interior and exterior, and some are just interior, and so on. So you would use interior on what you own, your own routers. You determine where the routes are located. You control the logic topology. You control the physical topology. You control the interfaces. You determine the interior routing protocols that are enabled. You do all that because they're all interior to you. Exterior, between autonomous systems. That's what they like to call them. ASs, autonomous systems. And an exterior protocol for routing performed by the so-called internet backbone. In most organizations, exterior routing will be limited to a single router that connects the organization network to the internet via an ISP. So on that one router, you got that one interface, and it runs this exterior protocol. This router is often called a border router or an edge router. It's true. Large organizations or organizations with critical missions have multiple ISPs that give them redundant internet connectivity. So if you're somebody big like Google or Apple or IBM or any of these, you're going to have multiple routers that are connected to your exterior. Normally they'll call them their border routers, and they use those protocols out there for exterior routing. Most of that's not too bad. conceptually to understand, okay, that's what a router's doing. We divided it up between internal and external. You can statically assign a route by typing it in yourself, or you can have it discover it through dynamic, and you have a default route, which is like a computer's default gateway, and that's statically assigned. Now you get into routing protocols, and because things overlap in them, it becomes more problematic to learn. So first off, routing matrix. When we looked at matrix, like if I've got multiple paths, what should I do about that? Should I just choose one? Computers, right? If it's all random, and this is kind of the thing, like a lot of times people will be asked in a lower level programming class to do a dice rolling game. And if it's to be truly the way it works in reality, which we say is random, you always have to add in a little factor that's actually not random. Because if it's totally random, really random, which computers can do, it may roll 10, 10, 10, 10, 10, over and over again, because it's truly random. It's weird, but it happens. And so on a computer, if you just said, just randomly send data out whatever port you want, it may just use the same port all the time, even though you've told it to randomly do it, right? So instead you have a metrics that will figure out what to do. And these are the characteristics. So these are the general characteristics of the matrix. All right, so you have a hop count. And again, that is how many routers do I need to go through to get to my destination. You may have, for instance, if we're going from Arizona to Washington, D.C., a router in Arizona may go, I got 10 hops to get to Washington, D.C., but this other way I've only got 4. Right, so 4 would be better. That would be better. And then for anything that's directly connected, the hop count will be 0. And then you have bandwidth. So bandwidth describes how big is that pipe. So how much. So you have to think of the data that you're sending like water. I've kind of mentioned this before. Bandwidth is how big is the pipe. Throughput is, get the backwards there. That's the measure of the capacity of the link. The throughput is the advertised bandwidth as the maximum capacity of the link. So the throughput will be less. It's sort of like saying, well, with this maximum pipe that I have, in reality I get this much out of it, and it goes this fast. The water flows this quickly or this slowly. That's what latency refers to as the slowness. And then how much is it used? Right, the link utilization is the percent of the network's bandwidth that's currently consumed by network traffic. The load is the load on a router that refers to the amount of computational work that it performs. So let's just deal with those first. You can see that if you're really a router trying to figure this out, you may actually have a faster connection through your 10 hops than your 4. So if you originally just did everything by hop count, what about the bandwidth? What if the 4 links are actually really slow and you have no throughput through them, or the link is totally utilized? So the hop count's 4, you got tons of bandwidth, you got tons of throughput, but it's 80% used, meaning it's slow. Or the routers it's going through are totally loaded, so the chances of them getting time to process your information is going to be lower. So sending it out through the 10 hop is going to be better off for you. So it's taking all these matrices and trying to figure out which is the best at that moment, right? Because that's all going to change. The MTU is the maximum transmit unit setting on a router that determines the maximum payload size of a frame. You can see that on your wireless routers. And then packet loss. So there's a ton of packet loss that's coming off of one of those links, and that may be because it's just so utilized that it's just dropping packets everywhere. Latency, the delay in the transmission over the path. So even though it's super fast, once it gets going, it takes a minute to kick on. And then reliability, the measure of how much the path is actually down. So all that's depending on the the routing protocol, all that's used. In some, it's only used, some of these are only used a little bit in some, and most of them are used in all of them. So it depends. But it's going to figure that out as it goes through every single time that it's connecting. So there's two primary categories of gateway protocols. There's distance vector protocols and link state protocols. And a third category is actually a hybrid. They try to combine both of those. So here's the difference. How is the matrix value calculated and how the path information is shared. And so here's distance vector protocols. What do? They set the metric value or cost based on how far away the network is. And that's typically measured in that hop count. May measure distance by delay, packet loss, or something similar. Set a direction that is associated with the distance. Direction refers to the network interface that is used to forward the packets. So when you're saying direction, you're saying, oh, that's going out port 7. All right, when using distance vector protocol, a router will only share information with its direct neighbors, the next hop routers. So distance vector protocols, you're all my neighbors, I'll give you that hop information. Nobody else. It will share all route information that it knows about. Here's everything I got. This is everything I'm connected to. And that's directly connected routers, and routes learn from other direct connected neighbors. And it'll send that route information at a regularly scheduled time. Now, basically, if you're using this across many routers, convergence occurs when all the routers share a consistent view of what's happening. So convergence is a process where we're all in agreement. Basically, as routers, we all agree that this is how the table looks. All right, now here's link state. Link state protocols, also known as shortest path first protocols, they do this. The router examines its directly connected network links and assigns a metric value. The metric value is based on the status of the connection and may also include other factors such as bandwidth and delay. The router determines the neighbor routers that are connected by each network link. The router builds a link state packet that contains a list of the neighbors and the metric values of the link of that neighbor. Through the process called flooding, the router sends this LSP to all of its routers, neighbor routers. So it just goes, boom, here's all this information that I know. The neighbor routers in turn send the LSP to its neighbor, and so on. To eliminate looping, each router forwards the packet to every neighbor except the one it received it from. All right, so you're connected to 4 routers. You get information from number 1. You send it through 2, 3, and 4. You never send it back to 1. Using converged routing information, the router constructs a complete map of the routing topology. From this map, the router will calculate the best path to each destination. Best path is determined by this algorithm, I can't even pronounce his name, which calculates the shortest path. All right, so using the link state protocol, the router uses the best path information to insert the next hop for each network path. Boil it all down, basically what we're saying is that, well, in link state protocol, it's actually trying to figure out the entire network. It's trying to figure out everything. And then it's going to figure out what to do about it. In our vector, it's going to say, this is what I know, I'm sending it over to you. The next one's going to say, oh, I got this from one of my neighbors. This is what I know, I'm going to send it over to you. And it sends it on down the line. But by the time you get to the third router down the line, in the vector protocol, it doesn't really know about the first one that's over there. It just really knows who to send it to for its direct hop. So link state routing protocols are going to be heavy. They're going to have a lot of data in them as they try to figure out the entire network, where distance vector routing protocols are going to be much smaller as they're not trying to figure out the entire network. And then there's your administrative difference that they actually assign these numbers, distance. And we're actually going to take a look at those those different routes. And then there's the commands for your setting your default route, which you did already in the first one you had to do. All right, now this has got a lot of information on it, a lot of different protocol facts for RIP version 2. What I'm going to try to do is give you the generals, because there's a lot of little details that are different on each one of these, but they all share, not all, they have many similarities. I don't want to say they all share similarities, because it depends on whether or not you're using distance vector or whether they're using our link state. All right, so RIP is totally distance vector. It's usually used for small networks, and RIP2 is classless. So remember that goes back to IP. Classful is basically saying we have to use 255.0.0.0, 255.255.0.0, right? We have to break it down like that. Classless means we can use 255, 255.128.0. If you don't remember any of that, and that sounds like what are you talking about? You got to go back to Unit 5 and look at that information. So enhanced interior gateway protocol is a hybrid. So it's going to try to use both of those in some sense to try to get the best of both use. So it's best suited for medium to large private networks, right? This one's best suited for small. So we don't have a lot we need to keep track of, so RIP is going to work for us. EIGRP, our network's quite a bit bigger, so we would like some of that vector stuff going on, because that's going to save us some time. But we also need something heftier. And then you've got open shortest path first, and that's a link state router, and it's used for large private networks. And is intermediate system to intermediate system. You can guess kind of what that means. It's best for large networks, supports large networks that use open shortest path first as well. And so you can kind of tell that, boy, there's some protocol stuff going on here, and there isn't one that fits the bill. Instead, what you have to do is look at your size and see what's going to be better for you. If you have a small size, then using is may not be what you want, because it's going to be heavy, right? There's a lot of data involved in that. And so larger networks is where you'd use those. These are not layer 1 routers, level 1 routers, level 2 routers. And border gateway. So that's between borders and trying to use ISPs, big internet service providers and so on. And yeah, there's a lot of details on this, and the tests will help you prep for the most important parts of this information, so pay close attention to the tests. If it was me, I would peruse this information, take a look at it, try to get it in my head, and then I would go to the test on the practice questions and see what's going on there. Right, that's what I do. Now, one of the most important things that we actually dealt with is NAT. And so I want to do a brief review of what NAT is doing for us. Because when you're dealing with IP, you have to do NAT with IP4. And so I looked at this in class. I can't remember who was there and who wasn't, but we'll go through a little brief on it again. So network address translations allows you to connect a private network to the internet without getting registered addresses for every host. So again, IP4, we've run out of numbers. So what do? We assign 192 numbers to every private network, or a 10 number to every private network. And then basically what happens is that we let routers figure out who's who. And so this is the process. Think about it. You're sitting on your network right now connected to this information, and your internal number is 192 something. But it's still getting out there on the internet and getting this from a correct server and sending it back to your computer that's using a fake number. Well, how does that happen? How does that occur? Well, we got to define a couple of things first. For instance, let's just take a look at how it translates. Hosts on a private network share an IP, address of the router, of the NAT router. So when we talk about a NAT router, this can be confusing to students because what they're trying to do is define out a service. So at home right now, as you watch this, you're connected to your little wireless router or your cable modem router or however you're connected. That is a NAT router. So it's providing that NAT service for you. So when you see a term like that, you don't have to think, wait, I don't have like 5 boxes. I don't have like a wireless router and then a router and then a cable modem router and then a NAT router. No. Everything's being done by one single router. And it's providing all those different services. So that's what it's saying here, is that it will share out an IP address or a pool of addresses assigned to that network. It depends. The NAT router will map port numbers to private IP addresses. And that's how it's going to work. It's going to use those port numbers, but not the ones that are publicly listed out there. So if you go to IAN and you say I want a list of TCP IP port numbers, there's between 0 and 65,000 numbers that you can use. That looks like a nice little list. All right, so it's got some of them on this list. And there are some that are out there that are recognizable, and those are the ones, right, that you have to actually memorize, like port 80. Port 80 is HTTP traffic, right? And you have to memorize a lot of these numbers, not all these. And then port 25, if we look at that, right, that's simple mail transport protocol. That's stuff that you have to memorize. Those are port numbers that are known on the internet, and this is what they do. That's basically what that's talking about. But there's also a whole nother set, because we've got 65,000 of them, that are just dynamic. And so what's happening is the NAT router is mapping these port numbers to your private IP. And so it knows, oh, they're talking to YouTube right now and doing this thing, and that's assigned to this particular computer. That way it can translate it back and forth. So technically speaking, NAT translates one address to another. Port address translation, PAT, associates port numbers with the translated addresses. Only with NAT, you would need a public address for each private host. So you got to use NAT and PAT together. And again, that's because it's basically taking your internal number and using the port number to track what you're doing. And then that way, when the data comes flooding in from YouTube, it goes, oh, okay, that's this port number that goes to this internal computer. That's what's happening. So there's different ways to do it. NAT supports a limit of 5,000 concurrent connections. So if you're a massive network, you're going to have several routers to go out. NAT provides some security for the private network because it translates or hides private addresses, but not really much. I always tell people that NAT doesn't provide you any security. That's personally my opinion. NAT router can act as a limited function DHCP server, assigning addresses to private hosts, which is what your little box does. And a NAT router can forward DNS requests to the internet, and that's what it does. And so then you have dynamic, which is very common, dynamic NAT, and that just dynamically figures out what it needs to do. That's what this is basically saying. It's basically saying that you decided to look on YouTube, and it said, okay, well, let's assign a port number for that, and let's get you going. And then there's static NAT, and that maps a single private IP address to a single public address. And that is also important. For instance, I can connect to EAC's email server. And how that happens is when I make a port 25 request to EAC's legitimate external IP number, it says, oh, port 25, that actually goes to this specific internal number. And so what you're doing is you're giving it this external address that the email server can be contacted on, and that maps directly to an internal IP address. And all businesses use that for, I want email to be able to connect to the outside. I want to have a web server, so I'm going to offer my web pages and host them out. And so I need people to get to that. And anything that's available on the internet for a corporation will usually have a static NAT, so that it goes, oh, web services go to this server, email goes to that server, that kind of thing. That's a static NAT. I usually in class have you do an assignment, and I actually write up on the board and say, how do we can make this work? And after you've gone through all the IP stuff and all the NAT stuff, I think the NAT stuff should actually be with the IP stuff. And then you can actually kind of visually in real world situation go, okay, I see how that's going to happen. If I say I want to access company web services, how does that happen? Well, it happens with a static NAT. It's called port forwarding. And then dynamic and static is where two IP addresses are given to the public NAT interface, one for dynamic and one for static. And that's the way that's assigned. Let me scroll down here. And then these, again, those are the reserved private addresses that we talked about quite a while ago. And then dealing with some troubleshooting. So the last section of 7 here. General routing problems. Symptoms is the inability to access hosts on a specific network or any remote network. So that's an important thing. When you do these troubleshooting things, so there's a couple of fine paths here, but if you do some troubleshooting ones later, you have to determine, can I get to that network at all? And what you're looking at, for instance, is, well, I'm supposed to be able to access this other network, and it's got 4 computers on it. So let me start trying to ping each of those computers. And so if you can't ping one of them, but you can ping the others, then that's not a routing issue, because you're getting to one of them. But if you have those computers and you're trying to ping one at a time and none of them respond to you, then it's probably a routing issue. You're not getting into that local subnet. Further, can't communicate with any host on a specific network, can't access the internet, remote clients cannot access network resources. So you realize that when it's describing all this, it's really talking about an entire network. I can't get to that network. That network happens to be the internet, or it happens to be a local subnet, or it happens to be network resources that I'm trying to get to from the internet, right? That kind of thing. So I won't run through all the different things that can happen here, but you can't access hosts outside the local subnet. So one or more hosts can communicate only with hosts on the local subnet. The problem is likely with the default gateway. So what this is describing is a situation where you sit down and you're like, I can't get on the internet. Let me see if I can ping my neighbor. Yep, I can ping my neighbor. Let me see if I can ping that other person over there. Yep, I can ping them. Let me see if I can ping something on the internet. Nope. Oh, what's likely the problem? The router could be down, right? But probably you have the wrong default gateway setting. So it doesn't know where to send that default traffic to, right? When it doesn't know what to do with an IP because it's not on your little subnet, it just fails. And understanding that process is where that really, really helps. So let's draw this one out just real quickly. Did I close that? I did close it. So let's reopen it. Oh, that's not what I want. Sketch. I did something wrong. Oh, there it is. Yeah, I did. I can't even tell you how long I've been doing these videos trying to get them ready for you guys. Okay. I'm not doing well. yeah, I'm reversing my E and K. What am I doing? I don't know what I'm doing. Okay, so let's just do a new one if I can. I'm not even sure how to. Ooh, ooh, that's neat. All right, well, I didn't save this, but it saved it for me. Isn't that nice that it did that? So let's go ahead and, I did not want to zoom in there. Sorry. Sorry you guys are just watching this. So let's just draw it right down here. So basically what you've got, we'll use Arizona and New Mexico here. So if this is a 190, let me write on the screen, 192 something. Let's say this is 192.4, and this over here is 192, I'm running out of space, 7. Right, so there's two different networks there. And so every time you sit down to ping, you try to ping 192.4 numbers and they all work. And then you sit down and go, well, let me ping 192.7 numbers, and they don't work. Right, so then that probably means, well, it doesn't know where to send the 192.7 numbers. Well, how would it know how to send the 192.7 numbers? Your computer doesn't have a routing table. It doesn't know where 192.7 is. So what does it do? Sends it to the router. And then the router goes, here's 192.7. So if your default gateway, that little example there just wasted time, didn't it? Isn't working, then it will never know where 192.7 is. So if multiple hosts are having the problem, check the default gateway. If all hosts have the same problem and the default gateway setting is correct, verify that the default gateway server is up. See, once you get to this point, I mean, this is simple troubleshooting. Let me ping that. I can't ping it. Nobody can ping it. Let me check the default gateway setting. Crap, that's correct. That means the router's down. It's not working for you. You don't want to have that happen. Then there's some other issues that could be the problem. Can't communicate with any host on a specific network, then that means that does not know the default, right? Use route command on the default gateway on the local subnet to verify that the router has a route for it. So you're looking at this point and saying, that's a network I know that I should be able to communicate with, and I can communicate with all these other networks, but not that one. Usually, honestly, that's going to mean the destination network is down. Something is caused a problem. But if you look up the route command and say, hey, what's the route for that? It should tell you what the route is. And if it doesn't have a route for it, that's why it's not making it. And then can't access the internet. Sometimes that can be that your DNS is down because people do it with names, right? But check that the internet is up and then check the default route. That's how it has to get out to the internet. They don't list the DNS problem, but I talk about it because nobody sits in their web browser and types 24.72. Right? It has to look up the name. And a lot of times it's the problem with looking up the name, that you never get a response from the DNS. So that's something to remember. And then opposite, the remote access clients can't establish a connection coming in. So if your remote clients are being assigned an IP address on the same subnet as the private network, make sure that the proxy ARP is enabled. And this gets into stuff that's, I mean, I have to describe a whole nother technology for you guys to really understand. So I'll make this one short. I'll make it as simple as it can be. They make it really simple, but it doesn't explain anything about why you would do that. And that's the problem. So if you're trying to get into your network and you have you've been set up, right? So it was working before, but now it's not. There's two ways to do it. If you connect to the firewall, then the firewall can leave your IP as whatever it wants and actually do basically the natting, right? And it'll let you access the server on the inside while your IP on the outside is different than what it is on the inside. But if you want to connect into the network, and some places do this, on the same IP. So you have an IP. I don't mean the same IP as somebody on the network. I mean the same network number. So you're connecting into 10, 10, 12, and you have a 10, 10, 12 number. So you're on the same network. And what's happening is the firewall is not doing the translation for you. It's just saying, oh, well, I'm just going to pretend like you're actually inside. And if you're not able to get in, then this proxy ARP is probably not working. You have to have somebody on the LAN that's basically saying, I'll be the proxy ARP for those people that are actually not on this network. And remember, ARP is address resolution protocol. It's a layer 2 thing that's actually aligning up your IP numbers with your MAC addresses. And so how does your computer that's not even on the same network know what MAC addresses to talk to? It has to have somebody proxy that. It has to have a computer that's aware that it needs to send that to some people. And if it's not working, then it's not going to do anything. In these kinds of situations, you're basically talking about, I want to sit at home and print to the printer on my desk at work, that kind of thing. And so they give you some information there, but they really don't give you enough to understand it fully. And I doubt I am too. This is, for me, this is a lot more difficult than actually being in class and doing it, because I can't see the looks on your faces. Most people won't say I don't understand that, but they'll get a certain look on their face like, I don't know what you're talking about. And then I can explain it further, and here I really don't know what to explain further. And so I will be having Zoom hours. I'll have that listed out there. And we can, you can just talk to me about it. We can also set up a class time, right? So we could say, hey, on 9 o'clock on a Thursday, on whatever Thursday, let's just set up this time and talk about this stuff. I would rather you have, listened to this lecture before we do that. That way it'll make more sense to you. But those are things that we just may need to do with these concepts that are really kind of difficult to understand. That's why I usually don't teach this class online, because I did once and everybody was like, I don't get it. And that's even with all the tools that are in here, right? That's even with, you can watch these videos, and some of their videos are really good. Some of them leave out a ton of stuff, but some of them are really good. So anyway, that is that. Turn in the notes for it. And again, we may need to do face-to-face. Make sure you're emailing me and letting me know how things are going. Don't just sit out there and suffer. I'm here to help you learn this stuff and get through it, not die in the process, right? All right, take care of yourself.